In my last video, I mentioned the Relu activation function, which looks like this, and its equation is the max between 0 and our input x. This simple function gives one solution to a big problem in deep learning and allows neural networks to have multiple hidden layers and fully utilize them. But first, let's understand the vanishing gradients problem. It is when, as the number of hidden layers increase, the weights and biases in the first few layers get a tiny amount of training relative to the layers near the end. First, we need to quickly look at one of the key algorithms behind how a neural network learns. It's called gradient descent. Let's take this quadratic graph. Say we want to find the minimum of this function starting from a given point. We can take the gradient at a position of the red dot and adjust our input by the negative gradient and by some learning rate. We'll have our learning rate set to 0.1. And then we take a step by some delta x. If we repeat this a few times, we can move closer and closer to the minimum. I want to draw attention to some key points of the gradient descent algorithm, which is important to understand for what comes next. First, we find the gradient at a point. Then, we take a step in the negative gradient direction. And most importantly, the magnitude of the step we take is proportional to the gradient at the point. We take the output of a neural network and we can subtract it from the label and square this result. This gives us a mean squared error. It also gives us a function which gives us a value on how bad our network is at a certain task. We use the gradient descent algorithm to find a value for the weights and biases which minimize this error function. But this is where the problem arises. This is the equation for the gradient of the error function with respect to w0. The derivation of this equation is not the focus of this video, but what is important is that we multiply the derivative of the activation function together multiple times. To understand why this is a problem, let's look at the common activation function, the sigmoid activation function. Here we have the function plotted with its derivative in green. We can see that the maximum is 0.25. Let's go back to our equation and assume that whenever we need to find the derivative of our activation function, that it is the maximum of 0.25. We can see as when the layers increase, the gradient, which is required for learning, decreases exponentially in the best case scenario. This leads to the problem where the weights in the first layer of our network, W0, are being adjusted by a tiny amount. This reduces the performance of the network as it cannot fully utilize its first few layers. This is where the Relu function provides a solution. Its derivative looks like this, and because the maximum value is 1, and 1 raised to any power is still 1, we do not have the same exponentially decreasing effect as the layers increase. This allows our neural network to adequately train the first few layers and allows for more hidden layers which are utilized properly. To end off, while the Relu addresses the vanishing gradients problem, it does have a problem with dead Relu. This is when the activation of a node becomes negative for a variety of inputs. This can stop the learning of the weights before this node. To address this, we can use the leaky Relu, which introduces a small gradient for the negative range. This allows training to be done even when the input is in the negative and keep the nonlinearity.